Sure. Hello, hello, hello. Good afternoon. All right. Hello, Chastity. Hello, Vanita. I'm doing the chat. Uh, Good afternoon, Brian. Good afternoon, Genesis. Good afternoon, Chastity. Good afternoon, Sydney. Good afternoon, Vanita. Good afternoon, Ariana. Good afternoon, Natalie. Good afternoon, direct message person. Oh, and hello, Annie, and hello. I said Chastity and Renita. Okay, and good afternoon, Kaya. All right, let's get rolling. Good afternoon, Annie. Okay, let's get rolling. Let's not. Let's let people. Okay. Ah, and there's Kaya in the. I do love that. I mean, anyway, and there's Annie. Okay, and it's like the thing is happening. All right, awesome. Um, Awesome. Okay, I want to just get rolling because one day we'll finally just have two normal. I guess this week is almost normal now. Anyway, I just want to get rolling. Um, I apologize that you didn't have a synchronized class yesterday. Thank you for rolling with that and understanding, and watching the video. There will be a day at some point in the semester where I'm going to flip it. There will be a day where you have time off and the other, no, is that what I'm trying to say? No, I mean, where the other class has time off and they watch your video or whatever it is that I'm trying to say. But thank you for watching the other class video. And even though I'm all behind and even though I didn't put feedback at all or anything, um, I didn't directly respond. I totally did read all of your comments about the other video. If assuming you submitted them, then you have gotten back the points, I believe. And if you got back the points, the 15 points for your two prompts regarding the other class video, if you got the points, I could definitely tell you that means that I read what you had to say, even if I didn't say anything about it. And so I'm going to try to cater today's class a little bit in an attempt to clarify the things that you all were asking me to clarify. Um, I actually always love doing that. I love hearing like that, what you did or did not, appreciate or follow or fully get from the video. Okay, wait, so more people are coming in. So yeah, it does seem like, and one thing I really appreciate too, just a slight sidebar here. Many of you will say things when I ask you to comment on a video or a class or material. What a lot of you say something like, "Well, it all seemed clear, but I of course I need time to absorb. I don't really have a specific question yet. It seemed pretty clear. It makes sense, but something like I can imagine when I go to start applying this myself, it's not going to seem that clear, or I'd like to see more direct applications, right? And or I need time to absorb this. I'm sure it's not as clear as I think it is right now. Like I appreciate that recognition on many of your parts. You're right. I mean, that makes sense. Um, so in a way, that's what today is for. Like, I'm going to try to briefly summarize the conclusion that I think I landed on yesterday, that we landed on, that we in the video landed on yesterday. But then the idea, honestly, the idea behind homework two, which we'll start going over today, homework two gets very repetitive and very sort of exercisey in a way. But in a way, homework two is exactly that. It's like, all right, like let's sort of see some concrete practice with this new idea. Okay, so that's what we're going to try to get to is like dealing with homework two in a minute. Now that we're finally finished with homework one, um, um, however, let me ease my way into that by I'm going to attempt in a way to summarize uh, and really to address what some of the concerns were that I saw in those video prompt responses. So first of all, so this is going to be like in general terms. So first of all, if you look at the board right now, and hold on, and I apologize, I'm going to switch the screen before I forget. Hold on one second. Oh, and good afternoon, direct chat person. Yes, thank you. Appreciate it. Okay. So if you look at the screen right now, the white part on the screen, like the equations, in a way, the white part, if d2z dt squared equals negative omega squared z, in fact, let's even say this. Oops, sorry. Hold on, hang on. Just to make this even a little bit more. Okay, if d2z dt squared equals negative omega squared z, then z equals z naught cosine omega t. That bit right there is in a way the conclusion of yesterday. Right now that doesn't mean it's clear. That doesn't mean we've practiced it. It doesn't mean you like we all fully understand it. But if there's a punchline or a takeaway to yesterday's lecture, mathematically, it is that. It is if d2z dt squared equals negative omega squared z, then z equals z naught cosine omega t. Now, before I go any further, let's note a couple, and that is actually a big mathematical conclusion. Like that's actually a big deal, even just in math alone. Like even whether or not we're talking about masses on springs or physics or anything like that. So, in fact, let me pause and say a couple of things. You might notice that all the work we were doing in homework one and problem nine and everything that I said in yesterday's video, you might notice that was all about X's. And then suddenly here I've just switched to Z's. That's subtle shift number one. Yesterday was about X's. Now I'm writing Z's. Now that is not a typo. And it's also not meant to confuse you. Like, why did I do that? Because X, at least in the context of yesterday and of the last 3 weeks, what X has meant is position on a ruler, like on an in space. Oh my gosh. Excuse me for a second. That is really annoying. Hold on. Sorry. X has referred to number of meters along a particular interval of actual physical space that a particular mass tied to a particular spring was going to be traversing, right? X meant position in space. And we were looking to solve for X. We were looking for like what position will the mass be at a given moment in time, right? Like it's a very physical, real question. But then it led us to have to do all this kind of abstract math. And I don't mean hard or easy, I mean abstract. Like we thought we were talking about a mass on a spring, and then because we did Hooke's law and we did F net equals ma, and we reminded ourselves of the definition of instantaneous acceleration. And the next thing you know, it's this thing, this mathematical relationship that I'm calling a differential equation, right? Like that's what happened yesterday. And then we go on this journey to sort of solve a differential equation, which many of us have never done before, right? And that's part of my point. Like, and it is a thing to be done that we did together. And it's an odd thing to do. If you were following me, or to whatever extent you're following me, you would notice, and many people brought this up in like your video prompts. Like you notice that like I'm saying that I'm solving this equation, but first of all, I'm not getting a number. I'm like getting another equation. So that lost some people. Like the solution to my original equation was yet a different equation. How is that a solution? And then second of all, but it is. I mean, it is. I'm not trying to confuse you further, but I'm just acknowledging that it's like interesting and unusual or unexpected what we did yesterday. And then this solution that I got, how did I get it? I did literally guess and check. I mean, you could be more sophisticated and call it conjecture and verify, right? But ultimately, what I did was and in fact, I didn't just guess, I built a guess. Like I guessed, and then I refined the details of the guess, and then I argued certain other details of the guess, and then I had this like full guess that I was like, all right, that is my guess. And then I checked it, and then I said it was right. And then I said, that's the solution to a differential equation. And therefore, now that we have the solution, we can predict where this mass on this spring is going to be at a certain moment of time. Like, okay, so that's like the summary of what we did. Now, that is a lot, honestly. What it is a physics question then that sent us on a math journey and back to the physics question. So the first thing I'm trying to say today, when I rewrite that conclusion on this board, but I change the X's to Z's, the first thing I'm trying to say is that math journey itself was important and has like general like lessons to be learned and implications for us going forward as physicists or as mathematicians. Like there's a math conclusion embedded in there that itself does not care whether we were looking at a spring or a mass or not. It doesn't care whether we were looking at meters or seconds or anything. Well, seconds maybe, but not, it doesn't care whether we're looking at meters. So the first thing I'm saying is right here on this board is from now on, if we face this expression that is called this particular version of this particular example of a differential equation, if we ever face this differential equation again, the it doesn't matter whether the independent, excuse me, it doesn't matter whether the dependent variable involved is called X or called Y or called theta or called I, as in electrical current. Not only doesn't it not matter what the dependent variable is called, it really doesn't matter what the dependent variable is measuring. It could be measuring any quantity that depends on time. If any quantity that is measurable and depends in some way on time, if that quantity can be described by a differential equation of this specific form, then we're saying a solution to this specific differential equation will be this specific cosine function of that variable. Let me say that a little bit. So I'm saying, well, yeah, I'm saying pick any variable you want. Could mean position on a meter stick, could be angular position along the arc of a pendulum swing, could be value or like strength of electrical current through a certain kind of circuit, could be temperature in a weather system. If that dependent variable, well, first of all, whatever that is, let's call it Z. When I say Z from now on, that's what I mean. I mean a generalized term for an unspecified, measurable, time-dependent dependent variable, right? From now on, if the second time derivative, if the derivative with respect to time of the derivative with respect to time of that general variable called Z, if the second time derivative of that variable equals the variable itself, but times some kind of positive constant times the number -1, which is a mouthful, but literally if the time derivative of the time derivative of the variable returns the variable itself times a, a negative constant, right? If it does that, then we know that that variable must be oscillating, must be wiggling back and forth. The value of that variable must be wiggling back and forth in the manner of a cosine. We know, in fact, specifically that that variable will be described by a cosine function who uh, who that can be expressed particularly this way. Like before you get into the details of the omega or the z naught and all that, which we got to talk about more today. But the general thing I'm saying, the reason I've switched from X to, okay, in fact, yeah, in fact, I'm going to add a page to make this really what I'm saying so far. Hang on one second. Okay. So one way, what this says right here, I'm trying to in English summarize what the mathematical conclusion is that we're saying. I'm saying what it says here is in general, if the time derivative of some dependent variable is directly proportional to the variable itself with a negative sign, then the variable oscillates cosinusoidally in the manner of a cosine. Like that's a big picture of what we're saying. That any variable, so if you find a variable, and this is really not only the key to homework 2, but it's also the key to homework 3. If you ever see a variable described by that second order differential equation, and what do I mean by that second order? What do I mean by that second order differential equation? I mean d2 over dt squared equals negative times bleh. Okay, that didn't help anybody, did it? I'm I'm saying Pardon me for a second. Right. I'm saying, well, I'm going to move on in a second. But I'm saying whenever that differential equation describes any kind of variable, then the variable is a cosine function of time. Okay. That's what I'm saying. I'm saying, and specifically, that means that the value of that variable is going back and forth, back and forth, back and forth, is oscillating, right? Is cycling through values there and back, there and back, there and back. Um, and we know that immediately if the variable is described by that differential equation. Okay, let me be a little bit more. What we're doing with this math now is we are describing a type. Okay. We are describing a type of oscillation that is very specific and very reliable and very predictable. And from here on in, it's called harmonic oscillation. When I wrote at the bottom of this page down here, SHO, that's what I mean. I mean, from now on, this type of behavior, this type, well, yes, this type of behavior in a measurement that can be described by that differential equation and that can be therefore solved by that cosine expression, we call this simple harmonic oscillation. Now it's oscillation, SHO. We call it oscillation because it has a back and forth periodic cyclical type of behavior. Okay, so anything that acts cyclically we call oscillation. So I could be walking like homework one of physics 203, like I could be walking back and forth at the front of the room, and as long as I'm walking back and forth, or sort of, going there and then eventually coming back and then going there again and eventually coming back, we would call that oscillation. But I could and probably would do that very spastically. I don't have to, I could oscillate in a very sort of irregular way, like take a certain amount of time to go there and then a different amount of time to come back, et cetera, and go at one speed this way and a different speed that way. That would still be oscillation. But what we're now talking about in this class is the physical properties and mathematical features of harmonic oscillation. What does it mean to be harmonic oscillation? Well, it means any or all of the following. First of all, any system that can be described by that differential equation, which we stumbled on yesterday. Like, let me say again, like I'm not expecting that people came into this class like knowing already about differential equations or knowing that one or anything. I'm saying we were doing physics. We were minding our own business. We were like F net equals ma, F equals negative kx. Oh, A is the definition of uh, the definition of A is the second derivative of position with respect to time. A is d2x dt squared. So we just like put those two things together, and then we ended up with this differential equation, right? Yesterday was x's. Now I'm saying it could have been x's, or it could have been y's, or it could have been thetas, whatever it was. It was that the second time derivative of the variable equaled negative times some kind of constant times the variable, right? Well, any system that can be described by that differential equation from now on, we're going to call a simple harmonic oscillator. If it's described by that particular equation, it's not just oscillating, it's oscillating harmonically, which in simple terms means very, very regularly and predictably and reliably. I'll be more specific about that in a couple minutes, but it's a very predictable, reliable, constant form of oscillation. Now, before I go any further, I keep calling that equation a differential equation. A couple of people asked me about this in the video prompts. And again, like I'm not expecting that anybody has seen differential equations before, nor had Newton, nor had Hooke when they came across this. Okay, it's a new thing until it isn't. Or, yeah. So, what does it mean when I say a differential equation? Just to remind you, I don't just mean an equation with a derivative in it. I mean an equation where the derivative is presented as a function of the dependent variable. That is the key. What makes this a differential equation is that what we know already going into all this is that z depends on, in the case of the homework, x depends on t. We know in some way position depends on time. And those are the things we care about. And we know that what we want is some situation where if you plug in t, we can spit out x, right? But this equation that we got when we just put together Hooke's law and Newton's law, this equation that we got has x and t in it, or in general has some variable and has t in it. But and somebody else asking about this, but they're not packaged the right way. What we want is x by itself or z by itself on one side, and a bunch of other things, some kind of rule on the other side that tells us what to do with t. That's not what we have here. What we have is a rate of change of a rate of change of the variable with respect to time, and it's being expressed as a function of the variable itself. That's the kicker. I'm over talking this, but somebody like what's making this a differential equation is that right there. If it said, if it had said d2z equals negative omega squared t, then that would be an equation with a derivative in it. It still wouldn't be what we want. What we would still want is z as a function of t, but to unpack that would not be this big of an adventure. We would sort of integrate twice. It wouldn't be that big of an adventure. The adventure here is that the rate of change of the rate of change of the output doesn't depend on the input. It depends on the output itself. At least one person, one of you, in your prompt, in your writings about the video, at least one of you said this thing that I love so much. Well, I mean, no, many of you said many things that I love. One person said something like, "Oh God, oh yeah," one of you said something like, the differential equation, and you even like sort of vaguely apologized in a way for this, but you were like, in my head, I think of it as a vicious cycle. That's just in my head, but that's how I think of it. And the phrase was vicious cycle. I love that because honestly, that person who said in my head, this kind of equation is just a vicious cycle. Oh, your head is correct. Like that shows you do get not only what the thing is saying, but you get why we have to put so much work into unpacking it. Oh, wait, sorry. What does it say in the yellow box? I'm just kidding. Oh, independent. Okay. So sorry. There's a direct chat thing. Hold on. I will get. Someone's asking, what does it say down here? So I'm all over the place. Someone's asking, what does it say down here in the yellow box? And yes, it's unreadable. What it says, even though I haven't explained it yet, is IND period independent of amplitude is what it's trying to say. Um, so yeah, let me get back to this page. So, okay. So first of all, a differential equation is a vicious cycle. Always. It is. It always says the rate at which, some kind of rate at which the output changes is a function of, depends on not input, but output itself. That is a vicious cycle. In and when it's and there's many different differential equations in the world. This isn't the most simple. It's just the first one we see in physics. It's not like you can imagine a simpler one than this. A simpler one than this would just have first derivative, not a second derivative. But this is the first one we see in physics. I mean, in the physical world. So this is a differential equation. When this differential equation describes a system, then the system oscillates harmonically. This mathematical statement, remember, it just came from us manipulating Hooke's law. So what we're really saying is any system that obeys Hooke's law is a harmonic oscillator. So what we're really saying physically, the reason we're spending so much time analyzing masses on springs is because it turns out it turns out that a mass on a spring is like the simplest, easiest to picture example of this larger phenomenon that cuts all across nature and laboratory experiments. All kinds of things in the world obey a version of Hooke's law, are governed by a version of this differential equation, and therefore behave just like masses on springs. The point of lab 2, you did a simple pendulum, right? It doesn't look like a mass on a spring. It isn't a spring. I mean, it's a string, but it's not a spring, right? It's not horizontal. It's like in the arc of a circle, but you know intuitively, and you experienced in the lab that that every single thing that you decided from questions 1 through 8 of homework 1, all of these things that you decided about a mass on a spring, that it conserves energy, that at the middle equilibrium point it has maximum speed and therefore maximum kinetic energy, but at the end points it has minimum potential energy and minimum speed, maximum potential energy and minimum speed, right? That as the velocity is going up, the acceleration is going down. All of these things that you decided about the mass on a spring in homework 1, what we're now arguing is all of those physical discoveries and mathematical implications are true of any system that vaguely seems like a mass on a spring, as long as it precisely follows that differential equation, just like a mass on a spring. That a pendulum going back and forth doesn't just sort of kind of resemble a mass on a spring, it is mathematically mappable to a mass on a spring. And so is a certain kind of circuit, let's say called an inductor capacitor circuit. The current will flow back and forth and back and forth, oscillate cosinusoidally, just like a mass on a spring. And subatomic systems, like hydrogen atoms, subatomic systems will obey a differential equation like this, a version of Hooke's law, and it lead to a version of this second order differential equation called the Schrodinger equation, and therefore end up making up a huge part of your studies at the beginning of P-Chem next year, when most of you take that class called P-Chem, which is really sort of like quantum physics for chemists, sort of. But that's what it is. I mean, it's like introduction to quantum physics. And I'm telling you right now that half of that class is based on solving and unpacking a differential equation known as the Schrodinger equation that is describing harmonic oscillation that takes place at the subatomic level. Okay, I'm talking a lot. What else is new? I'm trying to say, and I'm trying to sort of answer different questions as I go, kind of. I'm trying to say that we started the semester thinking we were studying a mass on a spring. What we're really studying is a vivid central prototype example of this larger phenomenon known as harmonic oscillation. Harmonic oscillation is always governed by this differential equation. A solution to this differential equation is always that cosine function or some version of that cosine function. And of course we have to practice this more. I know I'm being abstract again, but I'm just, I don't know. I'm just trying to like review and refresh and address these things. And what it means to be harmonic specifically, like not just oscillate, but oscillate harmonically, it means that the system will oscillate, will cycle, will go back and forth at a rate that we might call frequency, or we might call angular frequency, or we might think of in an inverted way as period. Like it'll make a certain number of cycles per second, or it'll take a certain number of seconds to make a certain cycle. Any harmonic oscillator will oscillate, will cycle back and forth at a rate that is super constant. How constant is it? It's so constant that not only is it a constant that we're ultimately going to call omega, okay, and I'll get to that question too in a big way, but the constant rate at which a harmonic oscillator will go back and forth and back and forth, the number of, say, cycles it makes per second will ultimately be captured by this thing called omega, angular frequency. That omega is such a constant, reliable, defining characteristic of the system that it turns out it not only doesn't change in time, it doesn't get bigger or smaller as the system progresses, but it doesn't even depend on space. In other words, to answer the direct chat person, I'm going to ask in a minute whether I had, like the direct chat person asked, like, what is in the second yellow box at the bottom of the page? And what I'm saying is in the second yellow box, it says independent of amplitude, meaning, and I'll expand on this more as we go, but meaning that that omega term in the differential equation or in the cosine function here, the omega, like the cosine right before the t after the cosine, I mean the omega right after the cosine, that omega, which ultimately is going to capture the rate at which an oscillator cycles back and forth, that omega may be determined by physical parameters such as K and M for a mass on a spring, right? Like remember yesterday, one thing I didn't write here, but remember one of the takeaways yesterday was that omega turned out to be equal to the square root of K over M. I'm going to talk more about that again, and someone had a really good question about that in the prompts. But what I want you to notice right now is that even if omega was equal to square root of K over M, or even if you might have discovered in lab 2 that omega is like equal to square root of G over L, or like parameters that describe your pendulum there in lab 2, what it doesn't depend on ever for a harmonic oscillator, it doesn't depend on Z naught or X naught or whatever you call it. It that the rate at which an oscillator goes back and forth never depends on how much space the oscillator takes up. It never depends on the initial position um, or maximum displacement of the oscillator. That feature, right? And I'm saying, I mean, how do you know? Well, you don't know. I mean, I'm saying right now that omega is a constant that does not get determined by this other constant, Z naught. It and the fact that it doesn't is the defining is what distinguishes harmonic oscillation from just oscillation in general. That okay, I'll say it in English and then I'm going to move. So to answer the direct chat person's question, so what it says down here in yellow is independent of amplitude, meaning the a harmonic oscillator is a system that behaves like a mass on an ideal spring. That's number 2. And then 3, it says it's a system that cycles at a constant frequency independent of amplitude. A harmonic oscillator will make a certain number of cycles per time that has nothing to do with how big those cycles are in space. That's what we mean by harmonic oscillation from now on. Now, there's of course I want to go on. I want to get to homework 2 and all that, but it just reminded me somebody else asked a question in the prompt that I was just on my mind. Uh, okay, yeah. I want to take a little. Like 2 people asked me. Again, the goal is to get to homework 2, of course, but how do you? Oh, how do you do? Sorry, there's a way. Sorry, sorry. I'm gonna do this again. Okay, okay. Wait, what happened to my, sorry. What happened to my, um, okay. When we applied Hooke's law and Newton's second law and the definition of acceleration to a mass on a spring, we put them all three together and we saw, oh, this differential equation seems to be true, right? That's an equation. It has a lot of information in it, but it doesn't have the information packaged the way we want. What we want, and what we wanted, and what we want was x as a function of t. Now, in order to get x as a function of t, I built a very big guess and then I checked it. Now this raised at least three questions in the video papers. Like one person, or at least one person, really two people, basically said like, "How did you make your guesses?" Well, yeah, that's a good question. I mean, that's the art of the science. Like, in some ways, there's no way to literally answer that because they are guesses. But but they're educated guesses. The guesses came from experience, both with certain mathematical functions. I know I'm looking for a function, so I'm looking for a function of a certain kind. So it helps if I know the behavior of mathematical functions like in advance going in here. But the guess also came from experience in the lab or picturing lab data like you guys have, right? Um, I forget there's an easy way to just add a page and I can't remember it. Sorry, I'm losing my mind. Oh, could it be plus? Wait. No, there was. Sorry, I'm losing my mind. I just want to. All right, I am losing my mind. Um, um, so I'll put this back in a second. We wanted some kind of x as a function of t. A couple people asked me like, where did I come up with my guesses? And then also, And in a way, someone was like, is there any other way besides guess and check? And no, honestly, the answer is not. The really, for a differential equation like this, it doesn't matter how sophisticated you are mathematically or scientifically. If you're really sophisticated or you've done this a million times before, then you just know already the solution, which is part of what's happening in homework too. You don't have to rebuild the guess every time because you kind of have gotten used to it and you know it. But there is no way in the first instance to come up with this solution without making educated guesses and then checking them. But here's the thing. The educated guess was just that. It was educated. It wasn't out of nowhere, and it wasn't like an unfair guess. The main thing, just to say quickly to the two people that asked, um, the physically, cosine comes to mind literally because of what it looks like. Like the reason I considered cosine at all is because when I pictured this, I'm trying to figure out the relationship between what time it is and where the mass is. And if I've been in the lab, as you guys have, I know that, or even if I just answered the questions 1 through 8 on homework one, I know that the thing is going back and forth, crossing the crossing the equilibrium position all the time and doing it smoothly and simply. So the first kind of function that comes to my mind from picturing that is something like a cosine function. One person right, so that's not my whole answer yet, but that's like partly where did cosine even come from? It came from like I wouldn't picture y equals t squared because that's a parabola. We know from physics 203, like y, or y equals x squared or x equals t squared, whatever you want to say. Like that's like a parabola. That's something that's just going up and up and up faster and or going forward faster and faster and faster forever, never turning around. That doesn't seem right to me, right? So now I'm not saying cosine's definitely right, but I'm saying the reason cosine comes to my mind is it's the simplest, smoothest function I know that goes back and forth like symmetrically like this. One person asked me, wait, but why not sine? They said, why did you not, which is a very good question. They said, why did you not pick sine? And then they had a very smart thing. They said, did you pick cosine because it's an even function and sine is an odd function? Very, very good reason. Some of you are comfortable with what that means. Some of you are not. Let me say, first of all, the truth is, once you start playing around with constants as we are, I could make sine work. It's not that sine is terrible. Sine could actually work. And I like this whole even odd thing. Yeah, not everybody knows exactly what that means. But my short version of the even odd, the reason I pick cosine, not sine, really specifically and concretely, is because the sine of zero is zero. Sine, so this is sort of what the person means by being an odd function. Sine starts at the origin, so sine would be the perfect function to pick if, when the clock started, when the experiment started, this object was at the equilibrium position. And that is, some experiments are like that. But I don't think an oscillator is like that because if I place the mass at the equilibrium position and then started my clock, it's not going to go anywhere, right? So what I think is a more direct, simpler capturing of our phenomenon is a situation where something starts not at zero, but at some original position that we called x naught, right? And yes, that even function. So I pick cosine, not sine. But the other thing is mathematically, somebody asked me about this. The other thing I know about cosine from experience, or Hooke knew, or Newton knew, what I also know, and you just maybe don't know to care yet, or wouldn't have known to care. The thing about cosine is, did well, let me back. Let me again say, like, why did I not pick x equals 1/2 at squared or something? Well, the thing is, if you take x equals 1/2 at squared, I mean, first of all, it's the wrong shape, right? But second of all, if you take the derivative if you take one derivative of x equals 1/2 at squared, what you get is dx dt, otherwise known as v, equals at, right? If you take one derivative of 1/2 at squared, you take the power and you multiply it by the coefficient, right? You the 2 by the 1/2, and then you lower the power by 1. So you get AT plus V naught, which I might add is equal to V, if you think about it, right? That's one derivative. If you take another derivative of that, if you take a second derivative of AT plus V naught, you just get A, right? Now, is that interesting? Yeah, I think that's interesting. But is that what this differential equation said? No, this differential equation said, like our whole situation here, is we're looking for we are looking for an x such that when you take two derivatives of it, you get back itself. If you take two derivatives of 1/2 at squared plus v naught t, you don't get any version of 1/2 at squared plus v naught t. You just get a. However, so that's bad. But what's good? Good would be something like cosine, where you take one derivative of cosine, you get negative sine. You take another derivative of it, you take the derivative of negative sine, you get negative cosine. So you get back the original function with a negative. But that's exactly what we want. We want a function. That's what this thing is saying. It's saying, I want you to find some kind of x for which, when you take two derivatives of it, you get back itself times some kind of constant that might be 1 or might not be 1 times a negative sign. Well, cosine, I'm not saying so cosine's not the full answer, but cosine has that property that if I take two derivatives of it, I'm going to get back itself times a negative sign. It's looking good. Now, again, by the way, to the one person who asked me about sine, sine would work also. This doesn't prove it. So, and truthfully, we could make sine work. It just takes more work. Like it's not as natural or direct because sine of 0 is 0. But I'm not saying that the answer, this is why this is sort of a whole thing. I'm not saying we're getting the only answer in town. We're going to find that soon enough in homework too. I'm saying right now we're getting an answer that works and hopefully the simplest answer that I can imagine. So I think, so go back to the page. Hold on. I'm just, again, sorry, I guess today's turning a little bit into like accidental Q&A. It's just that you asked all the Q's last night rather than now. But if this all seems like all over the place, it is. But it's partly because I'm just literally like trying to address all the questions that I remember reading and finding, really good. Okay. So physically, I'm saying cosine comes to mind. Okay, great, Annie. Yes, one of them is just right. But mathematically, cosine responds to two derivatives in the desired way. This all right here, and then and I'm going to get Andy in 1 second, but I'm going to admit something in a second too. All of that is just to address, like, how did I even come up with cosine in the first place? But then, then I admit, then someone asked, okay, but then why did you leap away from the K's and the M's and like start talking about omega, like out of nowhere? Like we had a K and an M, and then you just started talking about omega, and then you related omega back to K and M at the end. But one person asked, why did we leap to omega? Like, why didn't we just stay with K and M? Which is a fantastic question. I'm not saying that that person who asked that has anything to do with the person who's raising anybody's hand right now or anything, but that is a question I want to get to next, except first, a word from our sponsor. Yes, Annie.
Okay, Professor. So you're saying that you choose cosine over sine because the fact that sine gives out zero when we input zero is inconvenient for our situation, like the scenario that you constructed when you like created the question where like the mass is at 0.15 meters away when equals zero. Are you saying that because of our scenario we're not choosing sine
Okay,
for that?
so yeah, okay, great question. Number one. Number two, yes, that is what I'm saying. Keyword is convenience, because I'm really not saying that sine is wrong. I mean, I agree with you. It's not that sine could work. I just don't think it's as convenient. That's exactly right. Or at least it's not as convenient for like the first guess that I want to try. But then also, yes, you're right. It's not as convenient, and definitely the convenience is about 0, 0. But then one thing, yes, sine is inconvenient because in our particular situation, the mass happened to not start at position zero. But I also then want to say, since I'm trying now to be more general mathematically, I will say in general, if we have any kind of oscillator at all, in general, its initial value will not be zero because if its initial value is zero, it won't oscillate. So, yes, it was. So, all of this is like our homework one was like the vivid prototype example that inspires the whole general phenomenon. And so I think even in the general phenomenon, my first guess for situations like this will be cosine because in general, things are going to have an initial position that isn't zero. Otherwise, they won't oscillate at all, if that makes sense. Um, or hope.
Yeah.
Oh, yeah. Okay, cool, cool. So now, not to be weird, and I know everybody, this is all, but I do want to get back to like what I was trying to do. And let me say, in case we run out of time or whatever, or if you're feeling it all at any moment, like, wait, this went off, he went off the rails here. First of all, don't forget that, of course, I will upload this whole PDF, and you should look at it to see any pages, to see the pages in the order. And that's why I keep struggling, by the way. These pages will be in order, even, okay? And then number two, if really by the end of this whole discussion, you're like, whoa, that was not what I expected to be talking about, I'll say again, if you play the other lecture video, it might help. I mean, because it was a little bit more linear than this. But anyway, so I'm going to go back to my plan, but let me finish this one thing because honestly, there was this other question. Well, yeah, I guess I'll say very quickly. We 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 started. Yeah, here we are. Right. We started. Yeah, okay. We yesterday had this equation. We were looking for x as a function of t for the equation. We want it to meet or satisfy or be consistent with this. So then I guessed it's some kind of cosine, but then I left blanks, like in the yesterday video. I left blanks and said, okay, it's some kind of cosine, but that's too vague. Like there's going to be details here. And the way I thought about the details was in terms of units, right? And so a large thing I just want to say is like the units meant there had to be some kind of constant before the t and before the cosine. Like I just knew it wasn't good enough to say x equals cosine of t. It's some kind of cosine, but not just cosine of t, if for no other reason because you cannot take the cosine of a second. So I thought there's got to be something before the t that has units that will cancel out the seconds of t and leave appropriate units of radians. So just to address one of the questions that one of you asked, the thing that goes before the T, I don't know exactly what it is. Yes, what I do know from experience is it's going to have something, it's going to be a constant. So it's going to be determined by the constants that we know already. It's going to have something to do with K and M or some combination of K and M. Like, but I don't know. So the person who's asking, why didn't you just leave the K and M in there? Like, yes, it would be. I can know that the K and M are going to be in there somehow, but really, what I honestly don't know is how are they in there? Like, is it cosine of K plus M times T, or K divided by M times T, or N divided by K, or K squared? Like, I figure that if there's a constant before the T, yeah, it's got to be determined by K&M, but I have no idea in what combination, or actually, to be even more honest, what I know is that the way I'd have to put K and M together in order to make this thing is somehow their units they're gonna have to be put together in a way that their units all cancel out and become radians per second. So what I could do, and I think you sort of do in lab at one point, I could spend a lot of time sort of like churning and like trying, I could play around with units and try to make an educated guess as to how the K and the M come before the T. Or instead, what I did, so you could do that, but it's hard, Instead, what I did is I just said, I don't know what it is that comes before T. I'm just going to make up a new name. And this is what I want to encourage everybody. Like, I'm going to get back to the program now. Omega is what intimidates everybody for the longest time. Okay, it seems like a lot of this becomes about Omega for a while. And if in any way your brain is at all like, I'm kind of okay with this, but I don't really feel comfortable with this Omega business, join the club. Omega is, it seems like it came out of left field yesterday. And then all of a sudden it's everywhere. It did seem like it came out of left field because when I introduced Omega yesterday, it's literally just a name, a placeholder for something that I know very little about at the beginning. At the beginning, it's intimidating that I called it a Greek letter, but that's what everybody else calls it. I could have just called it D for Dan or something. It's just an unknown. What I know about it is that it's a constant. It's a constant. It's not a variable. And I know it has to have units of radians per second. That's all I know about it at first. But then when I do the math and I take the derivatives and I check, it turns out for everything to work, it's got to be equal to the square root of k over m. And if you on a side on your own time, if you check, you'll see that the units do work. Okay. So what I'm saying is I know there has to be a constant there. It probably is based on Canaan, but I don't know how until I get to the end when I check. I don't know if that answers that person's question or not. I feel like now, okay, I've tried to answer some of the questions I saw. If nothing else, let me just say the questions are very legitimate. If I still haven't answered your question yet, hopefully they'll start to get answered. But I know I have like 14 minutes left. So let me go on with the scheduled program. Um, um, which is homework two. Okay. Homework two, which is where we start practicing this and making it more concrete. Okay. So I'm going to homework two now. Um, and you'll notice homework two, once you get it, it gets repetitive and exercising, but at first it's not clear what it's all about. You do have to do the 5-step method. I've said to people before, like, you're gonna have to explain a lot at the beginning, and then you can explain less and less as you go once you've established the ideas. Okay, just notice one thing right at the beginning of homework two. It's trying to do what we did yesterday backwards. It's going straight. It's like, assume we already have a guess. Let's practice what it means to check the guess. Okay. So, in a way, the entire class that I did now was kind of addressing the where did our guess come from in the first place? Like, I don't know if it was clear or not, but that's what I've been trying to say for 70 minutes, whatever, 60 minutes is like kind of why we had to guess and where we got to guess from in the first place. But now assume we have again, right? And there's our guess right there. Homework 2, 1a. It says, imagine you have this function, x equals a cosine omega t, right? And it's going to ask you to take a couple of derivatives of it and then see if once you take the two derivatives, is this xt function, in fact, a solution to the differential equation that describes harmonic oscillation. Like that's what this, right? This question is literally just taking it's it's the check part of guess and check. And it's trying to say okay. So let's do the step method. Uh step so step one, here's my diagram and fact pattern. Now my diagram is a cosine function, a cosine graph. To a physicist, what it means to make a graph is you get across the basic shape of the relationship, the trend. You have explicitly labeled axes, and you have at least one point that represents like the scale of the whole graph. So I have that. I have labeled axes. I have a cosine trend, and I have one point labeled here, the point that we're now in this math example calling A. Yesterday or in the last 3 weeks, that's another name for what we've been calling x naught. It's the value of the variable at t equals 0. They have the same value, a or x naught. They're just emphasizing two different aspects again because we're trying to get more general now. What I thought of as x naught yesterday meant initially where the mass on the spring is, 0.15 meters from the equilibrium position. But then when I noticed after I went through all of homework one, is that where it initially was ends up being as far as it ever gets, right? That 0.15 meters turns out to be the place of minimum kinetic energy, maximum potential energy, the turning point, the boundary of this continuous oscillation that occurs. So the word for that we use in math and science is amplitude. Amplitude means like your maximum value. So the maximum value is the same as the initial value in a harmonic oscillator, but we just use one or the other depending on what aspect we want to emphasize. Okay, so I've labeled the amplitude, but then also before I go on to relate back to this whole discussion, what then? Whenever I do a diagram and fact pattern for any problem, the goal is for that every single constant or variable that's going to be used in the computations, every single constant or variable appears first as a label in the diagram. And that's the way of defining the constant or the variable before I go on and use it, right? So omega is being labeled here in this cosine graph. And what I'm trying to say is, and this is what, okay, partly to answer, like omega came out of nowhere. Omega is just some name for radians per second, right? For something that has to be measured in radians per second. But to say, and it has to go before the t in cosine of t. But to say that is to say a lot already. I mean, if you look at a cosine graph, what omega is a rate. I mean, radians per second is a rate. It's a rate. It's how frequently or how regularly this graph sweeps out radians per time, assuming time is being measured on the x-axis. Um, in other words, it's how wiggly the graph is, how frequently the graph will return to an original value per units of time on the x-axis, right? So if we define capital T, if capital T is means period, as right, even on this graph, the amount of time for a full cycle on this graph from one amplitude point to the next amplitude point. If that's what T is, then omega is the reciprocal of that, but multiplied by a factor of 2 pi. Like, like that's what omega is. It is the rate at which we carve out cycles, but scaled by 2 pi. Why 2 pi? And why radians? What why are radians coming in to a situation that is a physical object going back and forth in a straight line? Why radians if radians are a measurement of angle? Good question. Well, I mean, first of all, radians are coming in because we're talking about cosines, but and we're trying to impose cosines on this thing that's going back and forth in a straight line. But how does that all work? Like basically, what is this omega thing? Again, remember when we first introduced it, we just introduced it as a placeholder. But a placeholder that's measured in radians per second. So what does it mean to measure something in radians per second? Well, what I want to say is an angle is just a fraction of a circle. That is what a angle actually is. When it doesn't matter whether you measure it in degrees or radians or English, if you recognize, all of you recognize that this is a right angle, whether you call it 90 degrees or pi over 2 radians or a right angle, what you're recognizing is that this is a quarter of a circle, right? That's what it is, a quarter of a circle. And what you mean by that, what I mean by that when I say this is a quarter of a circle, what I really mean is it's a quarter of a circle no matter how big the circle is that I pick. It doesn't matter whether I'm right. That's that just that. So what an angle is a section of a circle divided by the radius of that circle. It's basically just saying an angle is basically arc length, except we're trying to say if you have twice as much arc length as I do, we don't want to say that you if I make a if you have twice as much arc length as I do, we want to call that a twice as big of an angle. We want to say that mine's a quarter of a circle and yours is a half a circle, assuming they came from the same circle. I don't care what circle they came from, but assuming they came from the same circle. If your arc length came from a circle that's twice as big as mine, well, it's automatically going to be twice as big an arc length as mine, and we wouldn't want to say that's twice as big of an angle. So in order to just be fair across the board, literally, we say that what an angle is an amount of arc length per radius. For each meter of radius that your circle has, however much arc length you carve out, that's what we mean by an angle. So an angle is a pure fraction of meters divided by meters, right? In the limiting, that's what an angle is a section of a circle. Specifically, and when you measure it in radians, you measure directly like that. Just arc length divided by radius. So if you go around a whole circle, the arc length is 2 pi r, the circumference, divided by the radius, you get 2 pi. So a full circle is 2 pi radians, right? From now on, a full circle is 2 pi radians. Pi is approximately 3. Just to picture this, I know it's exactly not 3, but just to picture what I'm saying, picture pi as 3 for a moment. Then that means to go around a full circle, you could say that you go 360 degrees. You could say a full circle is 360 degrees because you're used to it, but not because it literally makes any sense. That's just because it takes literally, where's the 360 coming from? It's coming from the fact that it takes approximately 360 spins of the Earth to make a full revolution around the sun. Like, why does that have anything to do with? I mean, there's deep, good historical reasons, but that's not what you're thinking. But anyway, you might be used to 360, but now we're saying get used to 2 pi. 2 pi is a full circle. Therefore, 6 radians is approximately is a full circle. So what is a radian from now on? A radian is approximately a sixth of a circle. Really, a radian is approximately 60 degrees. Really, it's like 57 degrees. If you want to know what a radian, from now on, a radian is an angle that's that chunky, like which you could recognize with no matter how big your circle is. A radian is like 60 degrees. What does that have to do with masses on springs? Is that just like 60 degrees is 60 degrees no matter how big your circle is? A radian is a radian is a radian no matter how big your cycle is. We're talking about oscillating systems, physical systems that cycle back and forth, even if it's in a straight line. From when we're talking about radians per second, angular frequency, omega, we're talking about if you made a cosine graph out of this, how rapidly the cosine graph would wiggle. But physically, we're just talking about how many round trips you make if you're the mass on the spring. Omega is how many round trips are made by the mass on the spring per second. Only each, only we're counting in radians per second rather than cycles per second. What's a radian? A sixth of a cycle. That's it. Like really a 2 pith of a cycle. But so Omega seemed to have come out of nowhere. It did. It was just a placeholder for this idea that is already true on cosine graphs. Omega is how wiggly a cosine graph is, how rapidly the cosine graph wiggles. In our physical terms, then, it's how many sixths of a round trip, how many sixths of a cycle does the mass or whatever make per second? If you're like, well, that's mathematical, but I want to be real about this. Like, can't you just talk about how many cycles it makes per second? Sure. If you physically want to talk about how many actual cycles per second is made by a mass on a spring, we call that standard frequency, not angular frequency, but we call that standard frequency. Is there a conversion factor between the two? And we measure it in cycles per second. 1 cycle per second is called a hertz. Is there a way to convert back and forth? Sure. Standard frequency, to get standard frequency, you just take angular frequency and you divide by 2 pi. In other words, and I know I have 1 minute left, if I say that this oscillator has an omega, an angular frequency of 4 pi radians per second, and that sounds like abstract nonsense, but it just means 2 cycles per second. Every 2 pi radians is a cycle. That's all we're saying. So an angular so I know it's 4:20. I'm just about to wrap up. So you can go from angular frequency to standard frequency, and then standard frequency, just flip that and you have period. If the thing is making 2 cycles per second, that means it takes a half of a second to do a cycle. So these omega, F, and T are 3 different ways to measure the same thing, which is rate of cycling. Okay. If you know one, you automatically know the other two. One is the most mathematically direct, the other is the most physically intuitive to all of us. And F, standard frequency, is the bridge between them. Okay, that's what omega is all about. I know we're done. So then what I did in the homework for that, of course, I'm going to pick up on this on Monday, but that was my graph. That was my picture. I don't expect you to have explained all of that, but that was how I labeled omega is 2 pi over t for that reason. And then it just asked me to do derivatives. So I did do derivatives. I'm just saying this quickly. You can go if you have to go, you have to go. But I'm wrapping up. I'm just saying in my step 3 of how to do the problem, I did lay out like I know in general in math that if the function is cosine of x, then the derivative is negative sine. And I know in general in math the chain rule. So I laid them out in general in step 3. I put them together in step 4, took the derivative, right? And then in the next part of the problem, I did another derivative. And I found that, oh, yes, when you take 2 derivatives of this function, you get back itself times the constant omega squared times -1. So yes, this function does what the differential equation demands that it do. So this, yes, is a solution. The guess works. This xt function is a solution to the differential equation. Okay, that's a lot. We'll do more on Monday, obviously, but hopefully that does something for somebody. Okay, I'm turning off the recording. I'm here for any questions, but other than that, have